Hello, welcome to Cloud. So we'll continue with structure determination from spectral data. This is our session 5. So we'll start with our next problem number 7 now. Derive the structure for a compound based on the following data. Elemental analysis is given, carbon 80%, hydrogen 6.7%. So from this we can find out molecular formula. IR data is given 1630, 1600. So 1630 can be for C double bond C stretching of alkene. Then 1600 can be for C double bond C stretching of aromatic ring. Then 1250, this can be for CO stretching. The 760 and 695, these are CH bending vibrations of aromatic ring of benzene, which suggest presence of mono-substituted benzene. Right, so this is the preliminary information we have from IR. Here they have given mass spectrometry data as well. So we have M plus molecular ion peak 120 is the molecular weight of that compound. Now we have PMR. In PMR we have 4 different peaks given. So first 3, if you observe these values, these are in alkene region between 4.5 to 6.5, and this 7.2 to 5H, this is in aromatic region. These are in aromatic region, right? So now we'll continue with this preliminary information which we have. So from elemental analysis we can calculate or we can derive molecular formula. This we have discussed in earlier session as well, so we'll quickly do this. So carbon, hydrogen percentage is given. Carbon is 80.0%, hydrogen is 6.7%, right? So if you make the sum of these two, it will be 86.7. So it is not 100. So whatever the remaining percentage we have, that will be the percentage of oxygen. So this compound must contain oxygen. So that should be 13.3. Right. So if we assume 100 gram of compound, it contain 80 grams of carbon, 6.7 grams of hydrogen, and 13.3 grams of oxygen. So assuming this, we will calculate moles of these elements, right? Moles of these elements. So for carbon, we'll get 80 divided by 12, 80.0 divided by 12.0. For hydrogen, it will be 6.7 divided by 1.0, and for oxygen it should be 13.3 divided by 16.0. So if you perform this calculation, 80.0 divided by 12, it will be around 6.67. If you divide this, it will be obviously 6.7. So 13.3 divided by 16 is 0.83. So these are moles of carbon, hydrogen, and oxygen. So after getting moles of element, what we'll do is we'll select smallest number from this, and we will divide all these numbers by that smallest number. So here this carbon will be 6.67 divided by 0.83. Hydrogen, it will be 6.7 divided by 0.83, and for oxygen it will be 0.83 divided by 0.83. So if you perform this calculation, we'll get carbon 6.67 divided by 0.83 will be around 8. Then similarly for H, 6.7 divided by 0.83, it will also come close to 8. Then for oxygen it will be 1. So we are getting this as a general formula. We can write general formula as C at N, H, 8N, and O, N, right? So if I take N is equal to 1, my formula should be C at H, 8, O, right? So we'll calculate sites of unsaturation for this molecular formula which we have derived. So we have 8 carbons, so that's completely saturated structure must contain 8 into 2, 16 plus 2, 18 hydrogens, right? So there is a deficiency of 10 hydrogens, 18 minus 8, deficiency of 10 hydrogens. So 10 divided by 2 is equal to 5. So site of unsaturation for this compound coming around 5. So this is matching with our preliminary observation. It may contain one benzene ring, so 4 sites of unsaturation for benzene ring, and it contain one alkene also, so the one site of unsaturation for alkene. So it's matching with the preliminary observation, so we can continue with this, right? Now this, there is one more method to calculate molecular formula. This is called rule of 13. So here in this case they have given a mass spectrometry data, so we have m plus value, right, which is 120 molecular ion peak, right? So molecular weight of the compound is 120, so we'll divide this 120 by 13, right? So from where we have got this 13 is they have taken one carbon and one hydrogen, so this 12 plus 1 is equal to 13, so they are dividing it by 13. So if you divide this by 13, we'll get quotient as 9. 13 nines are 117, right? So we'll get 9 here, and remainder will be 3. 120 minus 117, so remainder should be 3. So this quotient we will indicate by letter n, which is 9, and remainder is 3. R is equal to 3. So using this n and r, we can write base formula. So base formula will contain only carbon and hydrogen, right? So it can be CnH n plus r, right? So here in this case our base formula will be C9H9 plus 3, so it should be 12, right? So now from preliminary observation we know it contain CO stretching, right? CO stretching, so it may contain one oxygen. So what we'll do is in this base formula we'll add one oxygen. So when we are adding any element, we need to replace the atoms from this equivalent to this or atomic weight of this element which we are adding. So for oxygen it is 16, so we need to replace CH4 from this. We'll replace CH4, so 12 plus 4 will be 16. So we'll add one oxygen and replace CH4, so we'll get new molecular formula. So the base formula will convert to new molecular formula, which will be C8H8 and oxygen. We have replaced one carbon, so C8, and we have replaced 4 hydrogen, so H8. So this is new molecular formula we will get. So this is same as the one which we have derived from elemental analysis, right? C8H8O. So this is the another method to derive molecular formula. Now we'll continue with IR data. So in IR we have 1630. This is for C double bond C stretching of alkene. Then we have 1610. This is for C double bond C stretching of aromatic ring, right? So what you can remember is this C double bond C stretching of alkene will not come less than 1610. In very rare cases you will get this value as a less than 1610, right? So you should not get confused between C double bond C stretching of alkene and C double bond C stretching of aromatic ring. Then these two, 1250 and 1200, these are for CO stretching of ether, CO-C linkage. So we have symmetric and asymmetric stretching, so we get two values in this case. And then we have this 760 and 695. These are out of plane bending vibrations of CH of benzene, right? And this suggests presence of monosubstituted benzene, right? Now we'll continue with this. Here in PMR, in H1 NMR, we have 4 peaks. So if you observe A, B and C, what we have is we have 1H doublet of doublet, 1H doublet of doublet, 1H doublet of doublet, and chemical shift values are 4.5, 6.2 and 4.6. So this is in the region of alkene, right? So yesterday we had discuss in session 4, we have discussed uh, same kind of system, right? So here I'm writing H, 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 and this is X, right? So when we have this type of monosubstituted alkene, so this H, H is geminal. So if you need, we can write A, B, and C. So this HA and HB are geminal. So we'll get J geminal will be around 2 hertz. Here it is 2 hertz, so I'm writing 2 hertz. Then this is Cs, so we'll get J Cs. This is usually around 10 hertz. We have 9 hertz, so I'm writing 9 hertz here. And this J trans will be around 16 hertz. 16 hertz. So whenever you will observe this kind of pattern in coupling constants, we should be easily recognize that it must contain monosubstituted alkene, or this type of system present, right? This we can easily recognize. Now here in aromatic region we have singlet for 5H, right? Singlet for 5H. So this must be monosubstituted benzene. So there is one substituent and we have peak of all 5H which are given, right? So this is given as a singlet because it may be broad singlet, right? So we have this benzene and we have this fragment. So now we'll try to derive structure from this. So we have one benzene ring, right? And along with this we have one alkene fragment. We have one alkene fragment. We'll put the substituent as X, right? So along with this, it is all CH, right? So along with this we have one oxygen as well. So if you look at these fragments, what we can do is we can write this as a structure: CH, 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 O, and benzene ring, right? So this is your answer. Right? We have one monosubstituted alkene present. Now here in this case they have given mass spectrometry data. So this mass spectrometry data will help us to confirm the structure. So you can have a look at the structure. So this is structure for which M plus is 120. So it may lose one of the hydrogen from this system and we'll get 119. So this 120 and 119 we can easily recognize from this. Now you look at this 93, 77, 65 and 51. These fragments which are given. So for this 93 fragment is, I'm writing this here first. So this is benzene ring, right? So if you take a mono-substituted benzene, so we have 6 carbons. So 72 plus 5, 77, right? And we'll take one more oxygen attached to this. So it is 16. So if you make sum of this, it is 93. So that M by Z 93 must be this. So from this we are getting this 65. So how will we get this? This 93 will lose this CO and we'll get one 5-membered ring. So for this M by Z is 65 with loss of 28 carbon plus oxygen, right? Now another thing we'll see, 77 will be only benzene ring, right? 77 can be only benzene ring, right? Now this benzene ring will convert to this C4H3 plus with elimination of acetylene from this, so this C4H3 fragment which will get, this will be correspond to 51. So whenever you will see this fragment 77 and 51, you should identify this may contain monosubstituted benzene, or this 93 or 65 is benzene ring with oxygen atom. This we can identify when we look at these numbers, right? Okay, so here we have confirmed our structure with mass spectrometry data. Thank you so much.